Alright, so today we're going to just do a midterm 2 review. The goal of every review lecture, of course, is to give you just enough information to figure out where your weak points are so that you can go back to the actual lectures for those later. I can't give you every little thing in this lecture, but I can try to give you the biggest bang for your buck. Alright, so yeah, let's go in, let's start reviewing some stuff. So I guess the first thing I want to talk about is the pieces that make up a CPU, so all the little components that we learned how to build from first principles, from actual logic gates. And some of those you know how to build out of transistors now too, huh? But we'll just go down to logic gates. That's where we'll stop as computer scientists. But yeah, look at all these pieces. Alright, so we learned that we can pretty much build whatever we want out of AND gates. This is what they look like, right? We got AND gates. Look like the bullet from Super Mario. And we got OR gates, which are curvier and pointier at the same time. That's an OR gate. And then you got your NOT gate, or your inverter. Looks like this. Okay. There's others too, like exclusive OR is an OR with an extra little slash here, but that's good enough. But yeah, we noticed that we can build a lot of cool things. So for example, we noticed that binary addition was kind of happening with exclusive OR. Exclusive OR is more or less doing addition, alright? And so we figured that out, and that allows us to do 1-bit addition if we hook up our 2 bits that we want to add into an exclusive OR gate. But sometimes we need to carry, right? So we learned that. So 1, 0, let's pretend we're adding these guys to 0, 1, 0, 1. It's you're working on the first bit. You feed those into A and B here. And you notice that the answer is 0, right? Because they're the same. So exclusive OR is the right answer for the sum bit. 1 exclusive ORed with 1. That gives you the sum bit equals 0. That's your sum bit. Let me write that a little bit cleaner and a little bit lower so that I can do stuff above still. So yeah, 1 plus 1 really is 0, and 1's exclusive OR with 1 is 0. Maybe that's why it's a plus sign. Sum bit. And then, though, we needed to carry. Okay, we got to carry that one, right? Carry that one for next time. And so how do we calculate if we should carry out? Well, that's going to be 1 ANDed with 1. Or I'll use bitwise AND for that. Alright? Equals 1, and that's going to be our carry bit. Alright? And so you can build up these kinds of adder circuits. And you'll have to feed in a third thing. There's always got to be, usually there's going to be a carry in as well as a carry out for every other bit, right? Because now you have a carry in and 2 bits still to work with. So you need 2 exclusive OR gates, but more or less this is going to work out. Alright? And so isn't that fun? You can start chaining these together and you can build 32-bit adders, 64-bit adders, and now you kind of get at what's going on really in our modern day CPUs, which is cool. We talked about multiplexers. Multiplexers let you multiplex over, right? This is a multiplexer. It lets you choose one of these wires to be your output based on a selector value. And the selector value is sometimes, if you're choosing over 3 things, for example, you need 2 bits for your selector, right? At least 2 bits. And you can be alright, 0, 0, if you send in 0, 0 along the selector, there's really 2 wires here secretly. That means pick out A, you send in 0, 0, that's going to pick out A into your output. And you'll get that one, or maybe you'll encode 0, 1 means B, and if you give a 0, 1 to your selector, that means B's getting sent into the output. It's only ever 1 at a time, though. If it's 1, 0, that might mean C, or any other combination that you care about. And there's still 1, 1 left over. You just don't let that one be useful. That'll be a useless encoding. That's a don't care kind of thing. So yeah, it's a multiplexer. Go back to the lecture to see how to build it out of our individual gates. But yeah, let's see here. For adders, for example, the whole goal is to figure out how to build a small one, draw a box around it, and abstract away and zoom out. Okay, so for example, here's how you do a 4-bit adder. Here's kind of what that looks like. If you're trying to add these numbers, right? Add this number to this number, A and B. You got the initial carry in is 0. But you can start chaining these up, and it all is going to work out. And you feed in the output to a register or something. But it sees the 1 and the 0, right? And then a 0 carry in, and the answer is, well, it's 1. 1 is the answer, and there's nothing being carried out. 0 carried out, and that becomes the carry into the next 1-bit adder. Isn't that nice? Isn't that interesting? All right. So there's that. And then you got 1 plus 1 plus 0, so the answer is 0, but you carry a 1. Then you got 0 plus 1 plus 1, so the answer is 0, and you carry a 1. 0, carry 1. And then you got 1 plus 0 plus 1, the answer is 0 again, and you'll carry one more 1, and that is like potentially overflow now because we only have 4 bits, let's say. And then now you know how to make that, so now you've made a 4-bit adder. You can like chain a bunch of those to make a 32-bit adder, an 8-bit adder, whatever you want, okay? And so that's how you can add numbers. To subtract numbers, you will need to use the 2's complement form. So remember that like positive 1 is, let's pretend we're working with only 4 bits. That's equal to 3 zeros and a 1, right? To compute negative 1, the encoding of negative 1 with 2's complement form, you flip all the bits, 1, 1, 1, 0, and then you add 1. So this is going to be, it's an easy way to calculate what should negative 1 be, right? That's equivalent to negative 1. And so we're like, we give up 15 to be able to have negative 1. That's kind of the goal. All right. This first bit, your most significant bit, means it's negative if it's 1. All right. So that's the goal there. And you can prove to yourself like this works. So you can add that to 1, you will get 0 back. That's why we chose that encoding for our negative numbers. It all works out naturally. Okay. And so once we've got all this circuitry, we've got all these cool things, we like to put them in places. So one important place in the CPU is the ALU, or the arithmetic logic unit. So ALU. It is self-explanatory, right? It does arithmetic and logical operations. Arithmetic logic unit. And so it kind of does it all in parallel, which is interesting to think about. But let's say we got like we got a 64-bit CPU, right? So we got 64 bits of numbers coming in from registers, for example. And like eventually the answer that we compute within this giant box that is our ALU will also be 64 bits wide. It's like going out to a register, for example. To a register. We have X registers. Those are our biggest registers. Oops. Let me spell register properly. So there we go. Yeah, and so like what goes on inside the ALU is just like a bunch of different things. Like depending on what you want, A and B are being fed into all these at once, and through the magic of electronics, like it's okay to do them all at once. It's not going to waste any time. They'll all compute their answers. Like, okay, I'll do 32-bit bitwise OR. I'll add up A and B. I'll AND A and B. I'll check if they're equal to each other. And I've got all those answers waiting, and I'll pick out the one I want with a multiplexer. Right? I'll use my opcode, be like, all right, I wanted to AND them together or something. So I'll give in like 1, 0, and then that'll take the AND part into my result. Isn't that cool? That's kind of what will happen. And yeah, you'll just extract the one that you want, and that's like being controlled by the CPU, right? The decode stage is like setting up, okay, this is the opcode, that's the one, right? That's the one we're doing right now. So that's kind of how the ALU works, and also you're hooking into the result and going to like your condition codes are being calculated, like was the answer equal to 0, because like that'll go to like your flags. This is going to the flags, and that'll be set if it was like a flag setting comparison instruction, like your N, Z, C, and V, all those guys are being set like this, okay? And then like that's your ALU. You can have a bunch of these. You can do all these different operations depending on an opcode. And then the way that we draw the ALU, it looks like a pair of pants sideways. That's at least what I see. So yeah, that's kind of how that works. You package together all these things that you know how to build, and then you just like zoom out, combine them, because like with one of your instructions, it's only gonna be it's only ever gonna want to do one of these things at once. Okay, so that's the goal. And so yeah, all of your CPU is working together to execute whatever instruction you're trying to run, and kind of here's what's going on under that hood. Okay, so let's say, for example, we would like to run an add instruction. Let's say that that's what we're trying to do right now. So we would like to do an add instruction. Add, like, let's do into x0, x1, and x2. So kind of what's going on is what's happening in our CPU. There is like PC, first of all. PC holds the address of our next instruction. We go to memory. We figure out like, all right, go to the address in PC, across memory, we get back that it was an add. We store that in our IR register, all right? That's our instruction register. That's the first thing that happens, right? That's getting stored there. And then based on the value in our instruction register, that is like, who's looking at that? It's the control logic of our CPU. Okay, control logic is looking into that, and it's setting things. It's like, okay, I'm going to decode this. I know from the ones and zeros, it was an add instruction. And so I'm going to make sure, like, I'll feed into the selectors for my register file, because that's where all the registers live. Like, that's where X0 and X1 and X2 live, among others. They all live in here. So here's X0, here's X1, here's X2, all these bad boys. They live here, and so like maybe it's 1 and 2 live here. And then we're selecting them out, and they're being fed into the LU, right? That's kind of the idea. And then the control logic is also setting the fact that, okay, this opcode, this opcode that the ALU is going to perform on these inputs. I've hooked in X1 coming out of here, X2 coming out of here. We're going to do plus, give the opcode for plus, okay? That's the idea. Whatever opcode, whatever encoding that was, feed that into the ALU, because now we got the result coming out. That's kind of the idea, okay? And now the result's being fed along this wire, and it's going back to the register file, and we'll like set the write enable to high, so that, and we'll select out X0 as the thing that needs to receive the answer. And so then we got 3 coming out and into there, essentially, okay? At a very high level, that's what's going on. We're also like incrementing PC, of course, to like get to the next one next time. And then your comparison instructions are kind of doing different things. Remember that like if you do a comparison and then a branch, BEQ, for example, then that will change. Your branch will change PC potentially to something way different, like the address of a label or something. So yeah, but still it's this kind of idea. That's what's going on. Everybody's being fed in. There's a lot of multiplexing going on. And yeah, remember this, that there's stages, of course, but at a high level, that's kind of how you think about it. Isn't that fun? It's very useful. It's all working out one way or another. Okay, so yeah, with that, let's go to assembly for a little bit. Let's talk about like how to make functions, how to do recursive functions, and included in all that. So for our first example, let's make like a find function. Let's say we've got a C string, a constant C string, so that we can't change it. We're just going to use it. And we have a character that we want to like find within the C string. And what we'll do like a linear search. We'll find the first index where C appears in S, if it's there at all, or we'll return -1 if we could not find that character in S and we like got to the end of it. All right, we'll call it from C++. So I think just because I'll make a few files today, so let's make a folder for this example. We'll call it like the find example. So we'll make a find folder. And I'll go work inside of there for this first example. There. And so, yeah, I'll need two things, right? I'm going to need like a main.cpp file that like knows about it and calls it. Makes it easier for me. And we'll call this, and we'll do extern C so that we don't have to do weird label names. So there. So let's say, let's see out finding in hello world the character C. I don't think that character exists, does it? Then we'll search for some other things. We'll search for like an L, it'll find the first L, remember? And then we'll search for the exclamation point to make sure we're not like, we don't have an off by 1 error, because like we need to be able to find that last character. And then remember, by default, when you do 2 things between double quotes, you really are making a C string. So that is perfect. That is what we want here, even though maybe you didn't know before. So let's go and make, we'll call it find.s. That's what we'll do. Now I'd really like to steal some main function somewhere. Let's go to lecture 7 or something. Something small. Lecture 8. Surely there's a main function in there. Was there? Was there? Moment of truth. Oh yeah. That was a good guess. So yeah, I'll steal a main function here. And we'll just, or sorry, not a main function, but like, it's still a function. We're fine. We're fine. So here's all that, but it's not main anymore because it's got to be find. Okay? We'll change it. It'll be okay. So at least I've got assembly starter pack. Okay? What do I need to do here? I don't need anything in my data section. Am I going to call any functions? I don't think I need to. but I might need a saved register. Let's see here. Let's figure this out together. I don't think I need any of these, so we'll just pretend I don't. Let's just pretend I don't for a start. So we've got find, and oops, find. And remember what we're doing here is this guy. So that is like the signature of the function we're writing right now. And so eventually we would like to return an index, all right? So our goal is to look through this string s, which is sitting in, s is in x0, c is in w1. It's a character, so it's being passed along in a w register. That's the smallest place that we can access. That's just a byte. And yeah, so we're gonna move through s, right? Let's move through s, and we'll keep track of where we are. All right, so we'll start our loop, right? We're gonna have to loop and figure out, like, well, the first index of s is 0, so like we'll just keep counting up, all right? And maybe adding into x0. So let's do w2 holds 0. That'll be like, we'll use w2 to hold the index where we find the thing. Index in s where we found c. And so yeah, we'll just use that, and we'll keep advancing the x0 pointer into the string to like go and look at the next character, go and look at the next character. So let's make that happen. So I need a loop now. I need a loop, and I think the very first thing I need to do is see, like, look at the character that I see in the string and see if I'm actually like done with the string, because it might be like the string is empty. We always need to check and see if we're done with the loop, right? We're done with the loop if we found the character or if the string is empty. So let's get a byte at whatever x0 is looking at. Load a byte into w3, I guess. x0. So x0 holds the address of the next character to read each time. So I just read the next character out of the string. The very first time would be the very first character. And kind of what I want to do is I want to check, like, was this the end of the string? Was this the character I was looking for? Those will never be equal to each other, and so like we can check both of those. So let's compare against the character I'm looking for. Let's compare w3 to w1. All right, if they're equal, then BEQ, like, we need to return whatever our current index is. Like, that'll be sitting in w2, right? So we'll take care of that in just a second. We also need to watch out for the end of the string. So we also want to compare w3 with its 0. 0 is the null terminator character. For some weird reason, you can't do $\0. Like, it's really that is what we're checking for. And if that's equal, like, we're done. All right. BEQ. The string was over, but we didn't find the thing, so we need to like return -1. Okay, so that's important. So yeah, otherwise, if we didn't like return our current index, or didn't return -1, we're going to keep looking in the next index. The next index is one more than the old one, so we'll add into w2. So advance index and also the pointer into the string. So w2 and x0. So I'll add into w2 the number 1, and I'll add into x0 another byte to look through. All right, and I'll just keep on going. BAL to the loop. All right. So I will eventually stop the loop, right? Eventually, one day, and I'll either need to return the current index, or I will need to return -1. Right? And so those are going to be values that I'm placing in. So I'm returning an int. I'll be placing them in w0. All right. So I need to return an index. That's the thing that I'm holding in w2. That's always my index. So move into w0, w2. And if I want to return -1, I need to move into w0, -1. That's easy. Though I don't want to, if I'm returning the index, I don't want to fall through to here, right? So I need like a done label, and I need to BAL done here. So that's important. Yeah, otherwise, I'm done. I can just return. I didn't call any functions. I didn't mess with anything other than strats registers, so like LR is still set to the right thing, and I can just return. That should be good. Cool. So there's that, and I think that's a good start. I hope that is useful. And so here's like the relevant parts of the code, most of them at least, and here is the C++ code calling all that. So I'll just be lazy and give the main file and the find file, and we'll call it find. I think that's at least what I want to call it. Or I want a pattern here, so maybe we'll call it main. Let's call it main. Bam, and it looks like it's working. So C was not there, -1. L was 0, 1, 2, cool, that's the first L. And then exclamation point was apparently index 12, and I will trust that that is correct. Cool. So yeah, that's the first example. Let us next do a recursive factorial example. So with our base case, we'll do 0 factorial, just hard code that to be 1. We know the answer. And in the recursive case, we'll do we'll multiply it by our recursive call on the smaller input, but we'll multiply by our n, and that makes n factorial. Right, builds it up. All right, so I'll make another folder for all those. So I will call this factorial, and I will go work in there. I kind of want to copy in what I just did almost. Let's copy in finds like main.cpp to here, and then I'll copy in finds like find.s into a file in my current directory, and I'll call it like factorial.s. I think that would be useful. So let's go into main.cpp, because obviously it's a different thing that we're making right now. It's not find anymore. It's factorial. So it's got to be, it's still int, right? Int fact, or we'll call it factorial. Int n, okay? And then, what do I want to do? I want to call factorial a few times on like 5, let's call it like 4 times. We'll do 5, and 0, and 1, and 3. So like some edge cases and like some normal cases. Cool. And so now let's go to the assembly file, and it's not find anymore, it's factorial. Oops. Boop. And then it's going to be int factorial, int n. All right. And because this is a recursive function, I will be calling functions inside of this function. So I need to mess with the stack. I need to mess with the stack, and I'm going to need to save an answer for later as well. So, boop. Get rid of all these guys. I'll keep the ret, I guess. But what needs to happen is I better sub from SP 16. I will, at the very least, be saving LR on the stack, and I'll need to restore it later. So let's do this, opposite order. We'll load it, and then we'll restore our stack. And so I've got n, right? N is sitting in W0, and now I want to do my stuff. All right, so n is in W0. What do I do? Well, it's either 0 or not 0. So if it's 0, then I know the factorial. The answer is 1. All right, so compare W0 to the number 0. If it's equal, that's our base case. If it's not equal, let's like branch always, otherwise recursive case. But also, like, if it wasn't equal, it was not equal. So that also counts. That's maybe easier to think about. So like, all right, if it was the base case, what do I do? And then if it was the recursive case, what do I do? If it was the base case, well, the answer is 1. Move into W0, 1, and return. So BAL, go to the end of this function. Done, I guess. It's like here can be my done. Cool, so that's the base case. The recursive case, what we need to do is, right, we need to multiply our Rn, which is in W0, by factorial of n minus 1, yeah? And so, where's my n right now? It's in W0. I need to make this recursive call first, and I also need to place n minus 1 in W0, so that's kind of that's going to mess with everything, all right? So I need to save my n for later, all right? And it's going to get clobbered, so I need to use a saved register. So I'll store, we'll use x19, or it's going to be w19, but I need to save the whole thing. and SP plus 8. Then I need to restore it later. Okay, so now we're good. Now I can use W19 for this. So let's save our n in W19. Cool. And then now I can safely call factorial on myself. So I can call myself, let's BL to myself, with n minus 1. So W0 right now holds n. And if I subtract from that by 1, now, let's see, W0 now holds n minus 1. That's perfect. And so if I BL to factorial, which is myself, then I'm calling myself on that smaller input, which is cool. And now I get the answer back. Again, we're going to get the answer back in W0, because that's what happens when you call a function, right? So now, now W0, after all that, holds factorial of n minus 1 due to the magic of recursion. And it's our job to multiply that answer by Rn, which we saved away in W19, and that's our final answer. So mul into W0, because that's where we need to return from. The factorial answer by W19, all right? So that is going to hold the final answer, my n, right, times the recursive call of the smaller factorial into W0, and that's what I return. Cool. Making sure to save, or restore all my saved registers and LR. So now we know how to move, return back to whoever called us, which is going to be main in our case. All right, so here is most of the relevant code, and here is that main function calling us. So let's go ahead and compile those. We'll call it main again. So yeah, it looks like that is correct. 5 factorial is 120. Both of those are 1, and then 3 times 2 times 1 is 6. So that looks good. Nice. All right, let's keep on trucking. Just reviewing as much as we can. So let's go to the stages of instruction execution, because this is all pipelined, right, if you remember that. So the goal of your CPU is to do each little piece of execution in a small chunk so that we can eventually pipeline it. All right, so the first stage is called fetch. We're going to fetch the instruction out of memory. So PC is pointing somewhere, for example, right? PC is pointing into memory. We're going to read in our instruction, the bytes of our instruction, into our instruction register. It's a special place that we read our instruction into. Just like get the binary version of it sitting right there, all right? And then that's the fetch stage's job. That's all. It also increments the PC to be ready for the next one. And then we decode. That stage is all about taking what we just read, it's just binary right now, and figuring out like what was it really? Was it an add instruction? Was it a mul instruction? Like maybe it's add W0, W1, W2, or whatever. Okay. It reads those registers and it also sets the control logic. It's like, okay, hey, CPU, get ready. ALU, get ready. You're going to do a plus. And we're going to read out of these registers and write to this register. Like the control logic gets itself ready. All right. Then the execute stage. Dun, dun, dun. Actually, I have this picture. Let's go through the picture at the same time. So the fetch stage, what's it going to do? It's got PC sitting and holding some address in memory. Like that's where the instruction was. It's going to go read that out and shove it into IR as like a bunch of ones and zeros. Like this was the ones and zeros for this instruction. Okay. And then it's also going to modify PC to be 1, 2, 3, 8, I guess, 4 bytes later. And like you have an old value of IR that you're going to be like getting rid of and replacing with some new binary. Okay, so that's the fetch stage. Then the decode stage's job, right, was to like figure out, okay, yeah, it was an add instruction. That's what those ones and zeros meant. And like get ready, because I'm going to add in register 1 and register 3 together into register 0 or something, because your book is kind of backwards. Like the destination is the last thing. Like setting these multiplexers. It's giving them selector values. Isn't that interesting? So that's kind of cool. That's a decode stage. And then comes the execute stage. That just goes and executes the instruction. If like the ALU wants to go do something, it goes and do it, and it goes and does it this time. Okay, so execute is doing all that. Whee. So the execute stage is taking care of like, okay, we've sent in the add opcode somehow to this ALU, and it knows that it's going to add in like register 1 and register 3. and it's getting those out, like it's got those, it's being selected out of the register file, and it's ready to do the add instruction, and then it has the result coming out. So that's what it's doing in the execute stage. And then we have the memory stage, which is like go to memory and like read from memory or write to memory. We don't do that in the add instruction, but you might in a load or store instruction. And then finally, the write back stage takes a final answer and puts it in a register. It's all about the destination register and getting that set. All right, that's the write back stage. And it needs to be at the very end because like maybe you needed to get something out of memory. Maybe you need to do an addition, right? It has to be after both of those because only then do you have what you need to store. So here's the write back stage. It's like, all right, it's got the answer coming out of that, like it knows from the decode stage, like, okay, it's register 0 that needs to get set. And then it's got this result coming out of the ALU from the previous execute stage. And all right, we're going to set the write enable high so that we can set the register, and it knows like it's selecting out register 0 apparently. Like that's this one. It's going to go and shove the answer from the ALU into that one. Okay, that's the write back stage's job. And so yeah, they all work together in tandem, in lockstep, and they get all of our instructions executed. And the reason we split it up is so that like we can do each of these separately, like the washing machine analogy. We can pipeline them instead of doing it like this, like fetch, decode, execute, write back, but just like a bunch of add instructions. Instead of doing a bunch of those and using a bunch of clock cycles for each, you can start pipelining them. And like once you're done with the fetch stage of the blue instruction, you can move on to the decode stage of the blue instruction. The fetch circuitry is available to be used again now, so you might as well use it. All right. So that's what the pipeline is all good for. Like you can reuse these stages, like work on multiple instructions at once, right? You're working on 4 instructions at once by the 4th cycle, for example. And then, like after just a few instructions, you're starting to write back every stage. And so you really are every clock cycle finishing an entire instruction execution, unless you have to stall for some reason. You have to stall due to data hazards and control hazards. Remember that stalling is a thing, and think about why you might need to do it. Like you have some dependencies, or you might need to branch. You picked the wrong branch, for example. Let's talk about some data dependencies now, because that was important for us. You got read after write after read, and write after write dependencies. And their job, right, the whole reason that these exist is they're going to force you to like keep your instructions in order. You cannot rearrange them, because your CPU does like to do out of order execution these days. These force you to keep a pair of instructions that has this kind of dependency, one of these. Pair of instructions in their original order. You can't have the second one come before the first one if you have this kind of dependency. And so let me just show you a quick example of each of them, each of the 3. So let's say we've got add R0, R4, sorry, not R's anymore. Let's do W registers, W0, W4, W5, add W2, W3, W0. This is an example of which kind of dependency. We're going to, we're writing to W0, and then we're reading from it on the next line. All right? Does that make sense? This is a read after write, and that's the first kind. Read after write dependency. And what it's saying is, like, you cannot switch these guys. You cannot do it, because if you were to do that, do you see how this W0 would get the wrong value, get something from before? That's not okay. All right, so you can't rearrange those. Let's do a read after write dependency. So we got, like, I like my add instructions. We got RT, W2, W3, W0. That's supposed to be 0 at least. And then we'll do add again on W0, W4, W5. It's kind of the flip-flop, right? So we are reading, and then we're writing. So we're writing after we're reading, okay? Write after read dependency. And similarly, we cannot switch these. It won't work. Why? Because again, this add, if we put it down here, it would see a different value of W0 than the one it expected. It expected one from above, right? So that order cannot be changed. You can put stuff in between that don't touch anything, any of these registers, but like you you can't put this one before that one, right? You cannot change their relative order. All right, and then finally a right after right dependency. That's just like two adds to like W0. Add W0. I don't know, W1 and W2 this time, and like W4 and W5 this time or something. So these again, they cannot be swapped, cannot do it. This is a right after right dependency. And again, the reason is because like if you were to move this one downwards, then W0 would be set to whatever these guys' addition is, and everybody else who depends on W0 down here would see the wrong value, because everybody else down below wanted this value W0, whatever this answer was. Yeah. So that's why you cannot mess with them, because like somebody down below is going to be like add into like W7 W0 a couple times or something, and you need to keep this W0 value what it needed to be. Okay. So that's that one. What else? Yeah, we can pipeline our CPUs, make them fast, but we also want to be able to run a bunch of programs at once. So multi-core machines are a thing, of course. You got multiple cores, multiple execution cores in your single processor chip, and so you have the ability to run, if you've got like 4 cores, you have the ability to run 4 separate programs all at once, because they all are like mini CPUs. They have their own copies of registers, they have their own program counters in each of them. They're all running different programs, okay? Or potentially different threads of the same program, okay? So that's what a multi-core machine is all about. They all they have their own cache, each of them, L1 and L2 caches, and then there's like a shared L3 cache. All those fancy things going on to make our computers fast these days. So yeah, you can run multiple programs at once, and it really happens, all right? Though they're all getting switched out, right? Because you have like, if you can imagine, like your computer's running way more than like 4 or 8, right, programs at once. If you have like an 8-core machine, then you still need to swap them in and out fast. But this is pretty good. This is giving us more speed than we would have otherwise. All right. And then yeah, speaking of caches, let's talk about the memory hierarchy. Caches are right here between main memory and registers. They're faster to access. They're faster to access than main memory, and so it's like we'd like to get things out of there when we can. We don't have enough room for them, the data in our registers, right? So caches store at the level of like maybe megabytes of data, kilobytes for sure. Depends on which kind of cache. There's different kinds, right? L1, L2, and L3 caches. So let me draw that picture, and then we'll explain it. So like L1 cache is small, then you got L2 caches, a little bit bigger, then like L3 caches, even larger, all right? L1, L2, and L3. So yeah, caches, the whole reason they exist is due to locality in our programs. We want to keep things closer to the registers than just main memory, because we want to take advantage of the fact that like spatial locality is a thing. If I read one index of my array, I'm probably going to read the next index after it later, so I might as well load a bunch of things into my cache. I'll load an entire cache line, right? A whole block of things into a cache line. And then also temporal locality is important. I want to get things closer because I might be reading the same address in memory a bunch of times. Let's get in the cache closer to registers when we don't have room to place the answer in a register just yet. Okay? So yeah, L1, L2, and L3 are the standard cache levels these days. L1, we separate usually into 2 separate caches. You have an L1 instruction cache, which is read-only, essentially, and you have an L1 data cache for all your data memory, all right? Because instructions, like they might clobber data things, and you need both. You need both as your program's running. So it tries to keep them separate so they don't collide. But L2 and L3, there is no separation at those levels. So yeah, hopefully if you're looking for something, it's in one of your caches. If it's not, it's going to be loaded in through memory and copied into all the caches. Okay, that's the goal. And so yeah, this is you zoom in, like this is, for example, an L1 cache. It's being divided. Okay. So yeah, I think that's what I wanted to say there. And let's have like a quick little example of caching. Let's do a 2-way set associative cache, and we'll pretend we want to read these exact addresses in order. Each cache line can hold exactly 1 byte of data, just to keep it easy, just like your homework. We'll count the hits and misses, just like your homework as well, and we'll assume 2-way set associative cache with LRU replacement, every block is 1 byte. Every line holds 1 byte. All right. So yeah, let's say we want to read these things in order, and we have 4 sets to choose from. So the set that we pick per address we try to read, like where could it have gone in our cache, we're going to do mod 4, all right, for our address. So yeah, let's do 12. Like to read from 12 mod 4 is 0, right? So we're going to go to set 0. Hey, is 12 here? No, it's not, sadly. So that's going to be a miss. We're going to count them, misses and hits. So that was a miss. And well, we'll put it in here. Let's say we got empty room. So we'll put it in line 0 of set 0. All right, we have 2 options. And then 17, well, what's that? Mod 4, 4, 8, 12, 16. So it's 1. 1's left over. It's a miss, but we'll put it here for later. Hopefully we'll get it again. And then 3 is 3, set number 3. It's not there, so it's a miss, and we'll store it. 12, ooh, all right, we go to set 0. We're looking, both of these, is 12 anywhere? Yes, we found it, cool, so that's a hit. Nice. 5 is going to be 1, right? 5 is going to go to set number 1. We don't see it, but we have space for it, so let's just shove it there. Cool. And then we see 1. Ooh, uh-oh. So 1 would go to set 1. We look in both of these, they're both being used right now, but 1 is in neither. So, oh no. Let's see. Oh no, oh no. So we're on this one. By the way, 5 was a miss. Did I count that? This was a miss. 1, 2, 3, hit. 5 was a miss. Yeah, 4. I forgot to count it. There. So yeah, now we go to 1, and we have to evict somebody. So we can place the 1 anywhere. We can store it in the cache anywhere. Address 1 can go in either of these. It needs to go in the least recently used one, though. All right. So which is the least recently used one? It's going to be 5 versus 17. 17 was used longer ago. So we're going to shove out 17 to make room for 1. We're going to evict it. So that's another miss. All right. Then we got 13. 4, 8, 12. 4, 8, 12. 13 is 1 more. So oh no. Same problem. So we want to go to set 1, look in both of these. Oh no, 13's nowhere. So first of all, it's a miss. And we need to evict somebody. So we'll evict 5, because like we just read 1. 5 is the older one, the least recently used one. So we're gonna place address 13 there. And cool, we see 13 again, so it's gonna go to here, check both of these. 13 is in one of them. Cool, we found it, so it was a cache hit. Can read it quickly. And then we read 12, and that's going to go to set 0. It was there, and we were happy. Oh, sorry, 4. I forgot the 4. Excuse me, 4. We go to set 0 for 4. It's a miss, but we have room for it, so we'll save it for later. And because it was two-way set associative, now we come back to 12, which is going to set 0 as well. We didn't just kick out the old 12 or anything. We had room for both, and so we have one last hit. All right. So yeah, two-way set associative is slightly better in general compared to direct map, which is the other kind. Go study that one. Remember what kind it is. And then there's also fully associative. All right, there's also fully associative, and I do have an example of that one as well. We'll do it together at the very end. So get it brewing in your mind, and we'll do it at the end of these. All right. Let's have some more assembly examples though. Let's do a couple. Let's do one that just like does the echo command, if you've used that before, or just like use the cat command, for example. Let's make a program that just like, it's like a mountain where you shout out to it, it shouts back, it echoes back what you say. So like if you say hi, it says hi back. If you say hello, it says hello back. And we'll just do that until we see the end of file. So if you type the end of file or you give it an actual file, it'll just like repeat it back out to you. So it's kind of the equivalent of the cat program if you've used that before. So let's have that be our first example. We'll call it echo though. There is an echo program. We've used that, but it's not the same. It's more like cat. Let's make this just in the outer level. So let's steal a program with a main function, or just a program with a function, I guess is fine. It's good enough. Let's steal factorial, because that's using the stack at least. Boop. And then I will paste it into this new file. And this needs to be a main function though. Boop. So just like that, and I don't think I need any saved registers. I think we're good there. But I do need to restore LR for sure. and that should do it. So there's a main function, cool. And we'll make a program that just uses get char and put char a bunch. If you go and you look that up, that's these guys, right? In C standard IO. So go and look these up. They are here somewhere. Get char is like cn.get, and put char is like print a single character out. And so we'll use get char a bunch of times. It will eventually give us back EOF if we see the end of file character, and it'll be -1 as an int. Okay, so we'll watch out for that. So I think that's good. So yeah, this is kind of the equivalent of the cat program that we're about to write here. And so what do I want to do? I want to just repeatedly, in a loop, getting characters. So loop. I want to call get char. So use get char / put char to echo standard in back to standard out until EOF appears. So yeah, just call get char. It takes nothing, so I can just BL get char. I got the character in W0. Check. I need to check if it's EOF. If so, I'm done. I got nothing left to echo back. So compare W0 to -1, and if it's equal, we'll just be done. Done and return. Cool. All right, so there's that. And if we're not done, right? If we're still here, if we're not done. It wasn't EOF. We want to put that char right back out. Put the char back onto standard out. It just came from standard in, shove it back into standard out, right? And so we want to say BL put char and place the character that we want to put as the first argument, so it's going in W0. But actually W0 is the character still, so it's already there. It's perfect. The correct argument is already in W0. That is good news for us. So just BL put char. It's already in W0, and then we want to repeat. Repeat until we see EOF, and that check is always at the start. All right, so that's pretty much the code. Oops. Let's call it something normal. And so it should work. Hello, hi mom, Control D for EOF. And if we made an actual file, like we can do that too. If you made an actual file, like sample file.txt, we'll use this later anyways. We'll be like, the quick brown fox jumps over the lazy dog. That sentence with all the alphabet in it. You can shove that into the program itself, right? With this less than symbol. There, it's just gonna repeat it to you, essentially. That's kind of cool. So there's that one. And then for my second example, let's do one that reads a file, right, an actual file, a character at a time, converts it all to uppercase, and prints it all out. Okay. So we're going to use the C library still. We'll do fopen, right, to open the file. Where's all that? Surely it's here somewhere. Fopen and fclose, of course. Then we'll do fgetC, then we'll do just put char every time we get a character out of the file. But yeah, to get the file itself, we have to fopen it. And that gives us a file pointer back that we'll need to hold on to. Okay. So let's make that program. So I will be calling functions, right? I will be calling functions that are going to be messing with like the 0th argument and all that. So my file pointer, I need to hold on to it. So my file pointer needs to go somewhere. So I'll store that in x19 in a nice scratch register. And so I'll just make sure to restore it before I leave. And now I think we're off to the races. We're still going to need a loop. Still going to need a loop and a done and all that. But what needs to happen now? So the very first thing I want to do is like open the file. Let's use that sample file, that txt. Let's open that file. So let's open, no, but not in the loop, outside the loop, before. Open the file with fopen, and so it's going to be BL fopen, and the actual string The address of the string is going to go in x0. We'll place that in the data section. And then we also need to give a mode. We're going to open up in read mode, so we'll give a string, a C string that is just R. I'll just call it mode, and it'll be R. It's got to be C string though. There we go. So I got both of those. That's going in x0, and then in x1 is the mode. So 2 C strings, and then we'll open the file, and now we got the file back. It's in x0. fopen returns a file star, all capitals, file star. So it's a pointer, and so it's an x0. And I will save that in x19, because I'm going to be calling a bunch of functions. All right, so what am I going to loop now? I'm going to say, let's use fgetC to get a character out of that file, to read one char of the file, and we'll see, hey, was that EOF or not? So I guess I could have kept that code. So we'll move into x0, x19, right? That nice saved file pointer is right there. And then I'll bl fgetC. And now, now we have the next character in W0 or the EOF. All right, so watch out for EOF. So compare that character I just got in W0 with -1, because it's as an int EOF. BQ done. All right. Otherwise, if we're still here, convert the character that I just got, that I see in W0, it's a real character now, convert the character to uppercase with the toUpper function, and print it out. All right. So again, I want to uppercase the character in W0. That's my argument. Arguments go in W0 as well, so the character is already in W0, which is nice. So I'll just say bl toUpper, and now the uppercase version of that character is in W0, and now I can say bl put char, because again it's in the right place, and I will have outputted that uppercase character. And I just want to repeat that. Alright? And then once I'm done, right? Done includes closing the file, because we're good programmers. And that file was in x19, move it into x0, blf close. And I do want to return 0. Did I forget to do that in the other program? Move w0, 0. We like to return 0. I may have forgotten to do that here, and I did. So let's always remember to return 0 in our programs. There. So yeah, we got that one. And that should do it. Yeah. fopening, just checking our stuff, and repeatedly looping through our file until we hit EOF. So let's see if I can show you a decent amount of that. It's about as good as I can do. So yeah, /uppercase files, which it's hard-coded. We've hard-coded that the file we want to read is, here, let me split screen it actually, so I can show you the whole thing now, on the left and right. We've hard-coded that the file we want to read is the sample file, all right? So there it is, reading that file and outputting the all caps version of it, I guess. Nice. So yeah, that's a good second example for file processing. Yeah, let's move on to floating point. Don't forget that. The way that floating point numbers are encoded depends on the width, but they're all being broken down into like a sign bit, an exponent part, and a mantissa. So for 32-bit floats, F32 stuff, let's kind of break it down and fill up this picture, right? So first of all, the sign bit is 0 if it's positive and 1 if it's negative. If we're going to convert this number, it's got to be 0, all right? And now we'll convert 3.125 to binary. So 3 is 1, 1, and then 0.125 is what? So like the next character here would be this would contribute 1 over 2, right? 1 over 2, we don't want 0.5. The next one is 1 over 4, Python 3. That's just 0.25, that's still not enough. 1 over 8 to the negative 3, that's my 0.125. So it's going to be 0, 0, 1 in binary. Does that make sense? Okay, so that's the answer there. And then I would like to shift it so that like it's in binary scientific notation. So I want to like move this guy to right there. Okay, so it's got to be 1.00, sorry, 1.1001 base 2 times 2 to the what? We need to move it, if we put it here, we need to move it back. What it really was is 1 over, so times 2 to the 1. Okay, and then, all right, what is our mantissa now? That's easy. The mantissa is everything but the leading one. You drop everything but the leading one. So it's all these guys. That's our mantissa. It's 1001, and it fills up with 32-bit floats. It's 23 bits of all that. So it starts with this, and it's just a bunch of zeros after that to make up 23 bits. And then we had to shift it once, right? It's one shift. And so our exponent part, so that we can do positive and negative shifts, we do what's called, we bias it by 127. So we're going to do 127 plus how many right shifts, or minus left shifts. And so I'll do 127 plus 1, so 128. We got 128, and convert that to 8 bits of binary land, and that is this one. Because this is what? 1, 2, 4, 8, 16, 32, 64, 128's place right there. Cool. And then, yeah, the final binary number now, that represents 3.125 as a float, as an IEEE 754 32-bit float, is going to be, well, sign bit, 0, exponent, biased exponent, 8 bits of those, so 1, 0, 0, 0, 0, 0, 0, 0, and then our mantissa, 23 bits of our mantissa. So 1, 0, 0, 1, and then a bunch of zeros to make 23 bits total. All right, so that's what it's going to look like, and that is what you are going to never forget, hopefully. So yeah, we noticed that it was 1.25 because like this was the 2 to the negative 1's place, that was 0.5. The 2 to the negative 2's place, this one, was going to give us a quarter, 1/4, 0.25, and then 2 to the negative 3's place, we noticed that's our 0.125. That's the part that I need. Okay, so yeah, that's that. We do have floating point assembly operations. So let's talk about all this. So SIMD as well as floating point. So remember that remember the operations. Remember what SIMD is all about. It's all about running the same instruction, single instruction, on multiple data. So instead of doing 4 separate add instructions, like add these 2 registers into this third register, and then after that's done, add these 2 registers into this register, and do that for like 2 more. Instead of that, like make one big chunk of an instruction that works on a bunch of pieces at once. Add these guys into there, add these guys into there, add these guys into there. 4 things all at once. That's what SIMD is all about. Single instruction, a single add instruction working on multiple pieces of data. All right, so that's the goal. And so yeah, that is a very useful thing to have. We talked a little bit about SIMD assembly. We'll save that for the final exam. But there's also floating point assembly, and you can do SIMD floating point stuff as well. But for both SIMD and floating point, you have these registers. All right. So for floating point, you got D0 and S0, but you've got D registers and S registers. They're parts of each other, and you've got 32 of them. So you've got D0 through D31 and S0 through S31. They're all together though. Okay. And let's see here. Oh no, my PowerPoint stopped responding. That's not good. Okay, now it's happy again somehow. Yeah, so you got those. They're actually parts of a V register. V0 through V31 are the ones that really exist. Oh no, I got rid of these. There we go. So they're parts of those, and though when we're doing floating point stuff, we're only going to use up to the D registers. All right. So let's do Let's do an example where we get a double from the user, and we'll calculate 2 pi times that double. This would be like the radius r to make a circumference, or sorry, the area of a circle, right? Or no, it is going to be it's going to calculate the circumference. Yes, that is correct. Cool. I was right the first time. So yeah, we're just going to multiply 2 times pi times r, and we're going to figure out how to do this. All right, we'll figure out how to do it together. There is one interesting thing that we will have to talk about. So let's steal a main function, and this is a good one as any. and then we'll talk about floating point assembly. So what do I need here? I don't think I need x19. I always want to return 0. Don't need to restore x19 if I'm not saving it. And then, all right, so what am I doing? I would like to I need to get a number from the user, first of all. I need to make space for that. And then, let's see, I need pi as well. So I'm going to use scanf. All right, I'm going to say scanf. It's going to be %lf to read in a double for a weird reason. And then you need to give the address of like a number, num from user. So this is the scanf call that I'd like to do right now. So I'm going to need a format string, %lf. I'm going to need, let's see, this is the scanf format string. So I'm going to also want to print something out. So I'll use a normal format string for that. But there's my scanf format string. That's going in x0. And then I need to give space in memory to read into, and it's got to be a double. So where's that? Let's store that in the data section too. Let's get like the num from user. And you can do .double and store a double here, like 0.0, because we're gonna overwrite it though. Okay, so num from user can go there. And we'll do that. So that'll be x1, num from user, and then I can BL scanf. Make the call. And what that will do is it will set this, it'll wait for the user to type a double, and then it will set this memory to whatever double the user typed. All right? And then I want to multiply it by 2 and then by pi, whatever I got there. And I will show you how to do that. Remember that you can move things. Like I need to move 2 into a register. I can totally say like fmove into like d2, the number 2.0 or whatever. But I can't do the following. I can't be like move pi, fmove into like d2 3.14. Or even better, like 3.1416. This is too precise. It cannot be stored as part of the instruction, right? Because you only have a certain number of bytes to store the whole instruction, and 3.1416 is way too much. So I will put that in the data section, all right? This is not possible. But this one is possible. All right, so in the data section as well, I will store pi, or whatever version of pi I want. There. You can go crazier if you want, but that's a good one. So now, let's do our floating point assembly stuff, all right? So, yeah, like I said, pi is in our data section. We'll have to load it in to a D register. And I'll also need 2 in a D register, and I'll need to get my number from the user into another D register. And I'll be doing a bunch of fmols, right? So let's make all this happen. So let's get, well, I need the address of this number from the user, right? Let's do that in like x1 or something. Num from user. And I want to load into D0 the thing there. So there's my user's number. I want to do the same thing with pi, right? Let's do that as well. x1 gets pi. I'll put pi in, I don't know, D1, all right? And then I need also the number 2, or let's do this in 2. So that I can put in fmove into D1. You see how this is all going to play out? 2.0. So this is 2, pi, and r in D1, D2, and D0. Okay. So my goal now is to do the following. I'm going to multiply these guys together. So I'll do fmol into D0 eventually will be my answer. So let's do D0 times D1. That's going to be D0 is now equal to D1 was holding 2, so now it's 2.0, right? 2 times the old value times that r value. And, sorry, it's fmol, excuse me. And then I'll do the same for, I'll do the same with pi. So D0 equals itself times pi as well. 2 times, now it's equal to pi. 2 times pi times r. All right? That's what I just multiplied by. Cool. And now I want to print out my beautiful work, right? I'd like to print it out with a printf. So the format string for that is going to be format. It's going to be ASCII's. It's just %f for printing a double. It's weird. Scanf is weird, but yeah, I want to print it now. So I want to say like printf, %f new line, and then like the number from the user. something like that, all right? Or like star number from user, I don't know the best way to do it, because it's really an address, yeah, that we filled in. That's kind of what I want to call, so I'll load into x0 the printf format string, and then I need to get this double, right? This double is the next thing, it's the next argument. But here's kind of what's going to happen, right? The format string goes in x0 as usual, since it's the first parameter. But the second argument to printf, if it's looking for a double, printf expects the second arg, the second double arg. Well, let me just say double arg. It's the second argument for us, but it's the first double argument. It expects it in D0, all right? And that's where I put it, all right? And it's already there. So I can just say BL printf. I put it in the place that printf will expect it. All right? And so that should print 2 pi r. And we can check our answer. So it's waiting for me to print something, to type something. I don't know. Let's say that I got a 5.5 radius thing. All right, so let's check and see if that was the right answer. Times at 2, right? Yeah, that looks good. That looks very good. Very nice. So yeah, that is a good example of floating point assembly. It's just F. F is all over the place. But when you're loading, it's just a normal load. It's not like F load or something. That's the only thing. So yeah, go back to my examples from class if any of that was fuzzy. But this is just, these are all meant to be examples to figure out like which concepts are the most fuzzy in your mind so that you can go back and study those harder. Okay? So that's SIMD and floating point assembly. And yeah, the final thing is let me give you the answer to this. Let's do it together. This fully associative thing, which is never actually happening in real life, is just like a pie in the sky dream. But like this would be the greatest thing ever if it existed really. Let me solve this for you. All right? We'll do it together. Okay. So here are the things that are already there. And we have hits and misses to keep track of. We want to read all these bad boys. 41, 37, 49, etc. So I'm going to read 41 first. All right? Let's say I'm on 41. It's there. That's a hit because like you go to one side, you just look through everything. Cool. It's there. So that was a hit. Nice. 37 was a miss. All right. So now, what did we say? I think we said that we're doing LRU replacement, least recently used replacement, and like the lower ones, the lower lines have been filled in before the upper lines. So like, if we're getting rid of somebody, it's gonna be 40. Okay. It's gonna be 40 because like that's the oldest thing there. 42 is the second oldest thing there because we just used 41. Does that make sense? We just used 41, so now it's the most recently used thing. So it's 40 that's going to be evicted for 37 on a miss. 49, not there. And so, all right, 37 we just used, 41 we just used before that, so it's 42 who's going to give way to 49, and that's a miss. 45 is there, hit. 36 is not there, darn. All right, so it's... and then you can imagine we've used these guys. So what's the next oldest? The first oldest thing is 43. So 43 is given way for 36. We're evicting it. And that was a miss. Now we're on 43. Oh no, that was the thing we just evicted, of course. So we're going to place that. All of these have been used. So it's 44 is the least recently used one, according to our rules. That's a miss. Let me just make sure I've done this right. I should have 6 tally marks. Yes. 45 is a hit. 37, just like, is it anywhere at all? Yes. Hit. 37 again. Hit. 48. That is nowhere. So what have we used the least recent? Like, we've used all of these guys before, right? It's just 46 and 47 we haven't used yet. So it's going to be 46. That's going to be evicted. It's the least recently used thing for 48. And that is a miss. All right, so now 48's living there. And now it's 35's turn. Is 35 anywhere? It does not appear to be, and so I believe 47 is the last, like all of these things have been used so far in our diagram. So 47 is the least recently used one, 35 is going to take its place, and it will be a miss. All right, let me just make sure I've done 11 things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks right. All right, so now we're on 48. It's all going to set 0. You check every line with a fully associative cache. So 48 is somewhere. We found it, so that was a hit. Wouldn't it be nice if our caches were like this? Then we got 41, which is a hit. 45 is another hit. Nice. Good job, 45. 44, ooh, that's going to be a miss, isn't it? All right, so now this is the hard part. What is the oldest thing in here? All right. So, okay. We just used 45. We just filled up 46 and 47, kind of. 43 was right there. We used 43 here. 36 was here. 49 versus 41. 49 was here. I just used 41, so it looks like 49 was the oldest thing that's still in my cache. I think that's right. Yeah, so 49 is the thing that we're going to evict. That's the least recently used thing. And that, you just kind of have to work your way backwards. And so that's where I'm going to place 44 on a miss. Did I already count the miss or not? I'm not sure. We'll see. Let me just do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 things. Do I have 15 things? I don't. All right, so I needed to add a miss there. Okay, now it's 43's turn. That's a hit. Cool, because it's right there. 41 is a hit. Nice. Now 49. Uh-oh. So that'll be a miss. But now who is going to be evicted? All right, so we got who's in our cache right now. I see 37. Where was that? Let's just look at everybody. 37 was last used here. 41 was last used here. 44 is in my cache. That was last used here. 36, that was last used here. 43 is in my cache. It was last used here. 45, last used here. 48, last used there. 35, last used there. So it looks like 36 is the least recently used thing. And that's how we figure out who to evict. Usually you keep like a what's it called? You keep a track. You keep track somehow of like who is where. And sadly, I'm not allowed to undo anything right now. My PowerPoint is frozen. So hopefully it's still recording properly, but PowerPoint is very unhappy right now. So we'll try to wait on it and we'll see if it's happy in just a second. Can I close out and try it again? I think that's going to be what I need to do. So midterm 2 review. Because I wanted to delete that stuff because that was just my scratch work. All right. At least it's saved. That's a good start, I guess. Let's try to erase. Yay! All right, we're good. And so who we decided to evict? It was 36, right? So 36 is going away, and now it's time for 49 to take its place. And we already counted the miss, I think. Now we got two more. We got 48. Dun, 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 which is a hit. It's there. That's a hit. And we got 35, which is also a hit. So that's how you think about it. That's kind of how you draw and do your scratch work. And I think that was what I wanted to say about the review. So hopefully you found that helpful. And yeah, we worked through it all together. And now you know what you need to study harder for the midterm. So good luck as you're studying. Let me know if you have questions. And I will see you later.